Yeah, so at the time I was interested in string theory. So string theory had a big revival in the 1985, 86. I don't remember the precise date. And so many people started working on it. And my undergraduate advisor in Argentina was one of these that started working on it, and I worked a little bit on string theory in Argentina. When I went to Princeton, Princeton was the big center in string theory, and so I started also in this area. And well, it was interesting. We were a class that many of us were interested in this area, and there was some excitement that the superconducting super collider was going to be built, and then it was cancelled. That was disappointing at the time. Yeah, there were interesting questions. There was some anxiety of whether we would get jobs afterwards and things like that. I think that's a constant for most graduate students who start out. But in the end, it worked pretty well for us. Yeah, I was a bit interested. When I got to the US, I looked around what other things to do, but I decided to continue in this direction. I think it was well received. I think many people had the feeling, how could I have missed this? And yeah, they realized it's probably true. And then they started working on it. Many people started working on it and found more evidence for the relationship and found other applications. So, I mean, there were some people that were trying to probe it and say, maybe it's not true for this or for that, but then eventually, as various objections were overcome, people gain more confidence in it. Yeah. I think the basic translation between the boundary degrees of freedom. So the ADS-CFT correspondence relates a gravitational system that lives in the interior of some space-time with some particles or some quantum interacting system that lives on the boundary. And the basic translation between the two variables is not understood. It's not well understood. I mean, some aspects are understood, and you can compare some calculations. But the general translation formula between the two is not clear.
Tes 1, 2, 3, tes. Saya buka. Tes 1, 2, 3. Oke. So, okay.
Yeah, so at the time I was interested in string. so at the time I was interested in string theory. So string theory had a big revival in the 1985, 86. I don't remember the precise date. And so many people started working on it. And my undergraduate advisor in Argentina was one of these that started working on it, and I worked a little bit on string theory in Argentina. When I went to Princeton, Princeton was the big center in string theory, and so I started also in this area. And well, it was interesting. We were a class that many of us were interested in this area, and there was some excitement that the superconducting super collider was going to be built, and then it was cancelled. That was disappointing at the time. Yeah, there were interesting questions. There was some anxiety of whether we would get jobs afterwards and things like that. I think that's a constant for most graduate students who start out. But in the end, it worked pretty well for us. Yeah, I was a bit interested. When I got to the US, I looked around what other things to do, but I decided to continue in this direction. I think it was well received. I think many people had the feeling, how could I have missed this? And yeah, they realized it's probably true. And then they started working on it. Many people started working on it and found more evidence for the relationship and found other applications. So, I mean, there were some people that were trying to probe it and say, maybe it's not true for this or for that, but then eventually, as various objections were overcome, you get more confidence. The basic translation basic translation between the two variables is not understood. It's not well understood. I mean, some aspects are understood and you can compare some calculations, but the general translation formula between the two is not clearly understood. And this becomes even more confusing when you have black holes and you want to describe the interior of a black hole, and there are even bigger confusions. Yeah, so this paradox is a form of the information paradox, and it arises if you think that you have a complete description of the black hole as seen from the outside, that is unitary and respects the principles of quantum mechanics, and at the same time you have some description of the interior, some smooth interior, so the description that general relativity gives us of the interior. And the paradox arises because in order to have a smooth interior, you need the degrees of freedom outside the black hole to be entangled with the degrees of freedom that are inside the black hole. That's because when you have even the ordinary vacuum in here, the degrees of freedom in one you do an arbitrary division, the degrees of freedom on one side and the other are entangled. And that's something very important to get Hawking radiation right and so on. And on the other hand, you could imagine a situation where a black hole, well, we are saying that from the outside the black hole is like any other quantum system. So we could consider that black hole entangled with something else. And so the degrees of freedom, that situation, the degrees of freedom outside would be entangled with something else. And in quantum physics there is a principle of monogamy of entanglement. So you cannot entangle something with two different things. And this suggests that you could. And so that's the paradox. So then you think you cannot describe the interior cannot be smooth, perhaps. So with the Susskind, we pointed out the fact that when you have two entangled systems, they could be connected through some kind of wormhole. And so if that were the case, then when you entangle the black hole with some other system, there would be a wormhole that connects them. And then the interior of the black hole would be to the future of the left side, the system that the black hole is entangled with. It would be to the future within the wormhole. And then this principle of monogamy of entanglement does not hold when two of the systems are causally connected. So, I mean, if you have something here and something to the future, then those two things could be entangled with something else. So that's not a problem. So that sort of points some way in which this could be resolved.
Okay, test 1, 2, 3 tanpa mic. Lepas dah semua. Okay, tu dulu tutup kan? Okay, jadi. Tak ya, tak buka orang dulu. Ya, 14 minit tu.
Yeah, so at the time I was interested in string theory. So string theory had a big revival in the 1985, 86. I don't remember the precise date. And so many people started working on it. And my undergraduate advisor in Argentina was one of these that started working on it. And I worked a little bit on string theory in Argentina. And when I went to Princeton, Princeton was the big center in string theory. And so I started also in this area. And well, it was interesting. We were a class that many of us were interested in this area. And there was some excitement that the superconducting super collider was going to be built, and then it was canceled. That was disappointing at the time. Yeah, there were interesting questions. There was some anxiety of whether we would get jobs afterwards and things like that. I think that's a constant for most graduate students who start out. But in the end, it worked pretty well for us. Yeah, I was a bit interested. When I got to the US, I looked around what other things to do, but I decided to continue in this direction. I think it was well received. I think many people had the feeling, oh, how could I have missed this? And yeah, they realized it's probably true. And then they started working on it. Many people started working on it and found more evidence for the relationship and found other applications. So, I mean, there were some people that were trying to probe it and say, no, maybe it's not true for this or for that. But then eventually, as various objections were overcome, people gain more confidence in it. Yeah. I think the basic translation between the boundary degrees of freedom. So the ADS-CFT correspondence relates a gravitational system that lives in the interior of some space-time with some particles or some quantum interacting system that lives on the boundary. And the basic translation between the two variables is not understood. It's not well understood. I mean, some aspects are understood and you can compare some calculations, but the general translation formula between the two is not clearly understood. And this becomes even more confusing when you have black holes and you want to describe the interior of a black hole, and then there are even bigger confusions. Yeah, so this paradox is a form of the information paradox. And it arises if you think that you have a complete description of the black hole as seen from the outside, that is unitary and respects the principles of quantum mechanics, and at the same time you have some description of the interior, some smooth interior, so the description that general relativity gives us of the interior. And the paradox arises because in order to have a smooth interior, you need the degrees of freedom outside the black hole to be entangled with the degrees of freedom that are inside the black hole. That's because when you have even the ordinary vacuum in here, the degrees of freedom in you do an arbitrary division, the degrees of freedom on one side and the other are entangled. And that's something very important to get Hawking radiation right and so on. And on the other hand, you could imagine a situation where a black hole, well, we are saying that from the outside the black hole is like any other quantum system. So we could consider that black hole entangled with something else. And so the degrees of freedom, in that situation, the degrees of freedom outside would be entangled with the something else. And in quantum physics, there is a principle of monogamy of entanglement. So you cannot entangle something with two different things. And this suggests that you could. And so that's the paradox. So that then you think you cannot describe the interior cannot be smooth, perhaps. So with Susskind, we pointed out the fact that when you have two entangled systems, they could be connected through some kind of wormhole. And so if that were the case, then when you entangle the black hole with some other system, there would be a wormhole that connects them. And then the interior of the black hole would be to the future of the left side, the system that the black hole is entangled with. It would be to the future within the wormhole. And then this principle of monogamy of entanglement does not hold when two of the systems are causally connected. So, I mean, if you have something here and something to the future, then those two things could be entangled with something else. So that's not a problem. So that sort of points some way in which this could be resolved. But it's not a complete resolution of the paradox, because it's not saying really how the interior is constructed. Yeah, so you could think that it might apply, but we don't know how it applies and exactly what framework. So one possibility is that since we live in this expanding universe, that there is some theory in the far future that describes everything. But it's a little not very practical for us we are not living in the far future. So what that implies for us is unclear, and what kind of theory would. So these are the questions. I mean, my goal is that by understanding the interior of the black hole, we understand the universe that it's a bit like a cosmology, because the interior of a black hole is like a collapsing universe. And by understanding that, then we'll perhaps be able to understand an expanding universe like the one we live in. But we still haven't understood that collapsing universe in the interior of black holes. Yeah, so the Hawking radiation shows that black holes have a temperature, and systems that have a temperature have an associated entropy. And so when you calculate the entropy, it's the area of the black hole horizon. The goal is to explain it microscopically. And the first calculations, the first calculation was done by Strominger and Baffa, and what they did was to consider a special class of black holes, of so-called extremal black holes. So these are charged black holes, and in those black holes you can lower the Hawking temperature almost to zero, and you can then, when these black holes live in a theory with certain symmetries that are called supersymmetries, you can change parameters in the theory and transform the black hole into another object that is made out of some object called d-branes, into something simpler to understand, let's say, whose number of states you can count explicitly. So that was the strategy for the first calculation. And well, it gave an answer which coincided with the area, based on counting all the configurations of these objects. Well, yeah, I mean, there is a certain advantage to fashions in the sense that it focuses the attention of people, and they can all work together and talk to each other and not work in isolation. There is also this advantage in the sense that sometimes it's good when some group of people invest in a certain research direction for a long time and get really non-trivial results. And so I think it's, in a healthy field, it's good to have a balance of two things. Ideally, you would like people to follow different research avenues, talk to each other, and find common aspects and learn more. Yeah, let me add something to the previous question first. I think the extent to which now fashion is followed, I think is less than when I was a student, for example, because the community was smaller and it was more possible that people everyone did the same thing. Now I think the string theory is very wide, and there are many different aspects, and they're all being followed, and so But well, now going back to your
get everybody
Okay.
warmed up.
Right.
Right. Okay. Okay. All okay over there?
Yeah, everything well. How about
Okay.
there?
All right. Okay. Nice. Yeah, video is nice and clear. Audio is good. Yeah.
Mhm.
But my voice is clear?
Yeah, very clear.
Okay. All right. Good. That's nice. Okay. I think um, Secretary can replay the video. How's the weather over there?
Well, it's okay. Yeah, it's warm.
Warm.
Summer.
Okay. Oh yeah, summer.
Well,
Yeah. Right.
maybe
Yeah.
I should say
Correct.
hot, but yeah.
Okay.
I like it. I like the summer.
Okay. Which is nicer summer in States or in back home
In
in
Argentina.
Argentina? Yeah. Argentina is a
It's
bit
similar.
colder, right?
It's similar. Yeah, well,
Similar.
in Argentina, there are places where it's warm, places where it's
Okay.
not so
Okay.
warm. Yeah, it's a long country.
It's a long country. Yeah.
3,000 kilometers long. So
Yes. Yes.
it goes from the tropic to the cold.
Yeah. Actually, yeah. Right down to Del Fuego, Tierra del Fuego.
Right.
Yeah. That's nice. Okay. And busy with lectures?
They test well, I guess the screen sharing worked before, so it should work
Yeah.
now.
Right. You can do the test. Yes.
You can see it.
Yes. Yes. Nice. Yes.
Maybe I'll stop sharing it just in case you want to make an announcement.
No, I'll read your bio and all that stuff.
Oh, okay. Yeah.
We'll just wait a few more minutes for a bit more participants to come in.
Okay.
How is Nazri? How is YouTube going on? A lot of participants.
So were you asking me or?
No. I'm asking my colleague.
Oh, okay.
Nazri. No response. Probably is busy. Is it a busy time in Princeton? Exams or classes?
No, it's quiet time now.
Quiet time. Okay. All right.
Yeah.
Are you involved in any space observation projects related to black holes?
No, I'm a theorist. My
Theoretician. Okay.
very
So full
theoretical.
theory. Okay.
Yeah, I'm
Okay.
not involved in any observational aspect.
But don't they involve you in calculations involving what to observe, how to observe?
Yeah, as you will
Recording
see in the talk,
stopped.
my work is very theoretical about quantum aspects of black holes, which have not yet
Okay.
been observed or not close to being observed.
Recording in
Okay.
progress.
Yeah.
So full theory. Okay. We
Yeah,
have
I mean, there are other people here in Princeton who are very involved in the observational aspects. I have colleague who does the numerical simulations of the plasma around the black
Oh,
hole.
there is plasma around the black holes?
Yeah. So you have some gas that is ionized.
Oh, you mean outside the event horizon?
Yeah, outside the event horizon, it's going around, and
Okay.
that's the kind of thing we see. So it gets very hot, it emits light, and we get that light or microwaves.
Okay. So that's a lot of things to do there. Yeah. We have somebody on the chat. Good day, everyone. Yes, it's Prof. Siti Munyandi from University Malaya. Good morning. Thanks for joining. Yeah. Who else? One more. Jian Hulai. Good morning. Where are you from, Jian? Oh, from Malaysia. Okay. All right. Thanks. Nice for joining. Nice of you to join us. Okay. Few more minutes.
So Juan, is it your first invitation from Malaysia, right?
Yes, that's right.
Is there any country that you visit around Southeast Asia? Singapore?
No, I think the closest I've been maybe Hong Kong.
Oh, okay.
Yeah.
Okay.
I mean, I've been to Hong Kong, Taiwan, China, Japan, but not to Malaysia. Anywhere close, yeah.
No, as mentioned to you before, your field is quite interesting, but there's not many people in Southeast Asia working on that specific field.
Right. Okay.
But I think there's one guy who are quite famous in India. I forgot the name. Working also on I think you know him, right?
Or Sen, Ashok Sen.
Yeah.
Ashok Sen is.
I emailed him, but I don't know if he joined or not. But I know that's one guy who's doing some kind of black hole. So
yeah. Well, his works in string theory has done wonderful work there. Yeah, so,
but that's quite.
I also want to invite Shiraz Minwala. He's also probably would give you a very enthusiastic and energetic talk. So.
Yeah, I think we have one. I think in Xiamen University in Malaysia, there's one guy working on about your string theory and black hole. So I don't know he joined or not. Yeah, but he's originally from Singapore. He joined Xiamen University in Malaysia.
Okay.
I think this guy.
Hello, yeah. I'm the one in Xiamen University, Malaysia.
Yeah. Okay, thanks. Join this.
Bye.
Yeah. So I think probably you can start now. And later probably the
sorry, I was muted.
Yeah.
I was muted. Sorry. Thanks for joining, Yan Keng. All right. Okay. So
Thank you.
okay, if everything is okay, I will start now. Okay. Salam sejahtera, selamat pagi, and a very good morning to all gathered here virtually. We are here for International STEM and Innovation Colloquia Series 17. Thanks to the unending efforts of Drs. Nazri Halif and Sharifan Faiza. Thank you to UNIMAP Vice Chancellor Professor Zaliman Salli and Deputy Vice Chancellor of Research and Innovation Professor Rizal Fandi, their respective officers and broadcast control team at UNIMAP for hosting this event, as well as IEEE Sensor and Nanotechnology Council Malaysia for collaborating in this ISICS session, especially for Zoom. I'm Prabha, the moderator for this ISICS Series 17. And a very good evening to our distinguished presenter, Prof. Juan Martin Maldacena. Before we hear him, please allow me to describe a bit about Prof. Juan Maldacena. Prof. Maldacena is Carl P. Feinberg Professor in the School of Natural Sciences at the Institute of Advanced Studies, Princeton. He has also taught at Harvard University and Rutgers State University of New Jersey. Juan Maldacena was born in Argentina in 1968 and completed his undergraduate studies there. He then completed his PhD at Princeton in 1996 and has been a professor at the IAS Princeton since 2001. His research interests include quantum field theory, quantum gravity, and string theory. He has proposed a relationship between quantum gravity and quantum field theories that elucidates various aspects of both theories. He is studying this relationship further in order to understand the deep connection between black holes and quantum field theories, and is also exploring the connection between string theory and cosmology. All these has brought him many accolades, such as the 2022 Honorary National Mention of Argentina, the Galileo Galilei Medal in 2019, Richard E. Prange Prize and Lectureship in Condensed Matter Theory and Related Areas in 2018, Albert Einstein Medal and Lorentz Medal both in 2018, Breakthrough Prize in Fundamental Physics and Pomeranchuk Prize both in 2012, International Center for Theoretical Physics Direct Prize and Medal in 2008, American Institute of Physics and American Physical Society Danny Heinemann Prize for Mathematical Physics in 2007, American Physical Society Edward A. Boucher Award in 2004, Pius XI Medal in 2002, Sackler Prize in Physics in 2000. Sorry about that. The UNESCO Javed Hussein Prize for Young Scientists in 1999, MacArthur Fellowship in 1999, and Packard Fellowship, as well as the Sloan Fellowship, both in 1998. That's quite a list there, Prof. Prof. Juan will talk about black holes and the structure of space-time. If anyone wishes to ask any questions, you're free to ask at any time during the talk, but please raise a hand or type into the message box or YouTube Live. Prof, the floor is all yours now.
Okay, thank you for the kind introduction. So, okay, sorry about that. Can you hear me? Sorry, I pressed the wrong button. It was totally, yeah.
Okay, yeah, we can.
Enable, yeah. If you can enable my screen sharing again.
A minute.
By the way, you're free to ask questions anytime during the talk. So just speak up and no need to raise the hand because I won't see your hand.
Oh, if anything, I will interrupt. Okay. If I see anything, yeah. Sure, screen sharing, yeah, okay.
Okay, very good.
All yours, Prof.
Okay, wonderful. Okay, so we'll be talking about black holes and the structure of space-time. And we'll start with some very general, so the structure of the talk will be basically to recall some aspects of black holes, how general relativity implies that you have black holes, how black holes were confusing, even Einstein was confused about black holes. So you shouldn't feel bad if you're confused about black holes. So Einstein thought black holes couldn't exist, but they're actually an unavoidable consequence of general relativity. Now, there was another surprise, another confusion, is that black holes are sometimes not black. That was an important theoretical discovery by Stephen Hawking. And he thought that also there would be a conflict between black holes and quantum mechanics. But then now we'll see with more modern theories that black holes we think are compatible with quantum mechanics, and there is some interesting connection between quantum mechanics and space-time geometry. Though still there are some important puzzles regarding the black hole interior. Okay, so we'll start from sort of the beginning. We'll start with the principle of relativity, which says that an observer traveling with constant velocity observes the same laws of physics as one at rest. So we have someone in the lab. So let's say a person in his lab, and we have someone else that is going in a moving lab. Both, if they do experiments locally, they will see exactly the same laws of physics. This principle goes back to Galileo. Now, the new aspect that Einstein brought in was the idea that there is one more principle of physics, which is the idea that there is a maximum velocity for the propagation of signals, which is the speed of light, so that no signal can propagate faster than the speed of light. And that's one of the laws of physics. And so imagine that you have two observers, and we have some light. So this way we think tries to represent a beam of light. Naively, your everyday intuition would tell you that this observer who's here would see light traveling slower than the observer that is stationary. However, the principle of relativity is telling us that both should see light propagating at exactly the same speed. And the only way this is possible is if time flows differently for different observers. So the idea is that time sort of flows a little bit more slowly for the observer that is moving, and in that way he can measure the same speed of light. And in addition, the lengths that he measures are also contracted. That's why it's drawn here a little bit shorter than the other one. Now, this leads to some funny physical effects, such as the so-called twin paradox, which says that if you have two, let's say, twins that are born at the same time, and then you take one of them, let's say the one on the right, and we move it at very high speeds, and then we bring him back, then he will have age less than the other person who stayed without moving. So because time flowed a little more slowly for this person that was moving. Now, you might be confused because you might be confused about which is the twin that is younger when they come back, because there seems to be a symmetry between the two. But actually, there isn't a symmetry because this twin that moved to the right and came back felt some acceleration. So that's different than the one who stayed stationary that did not feel any acceleration. So the two twins are really different, and the one that felt some acceleration was the one that that is younger. Now, suppose that we make up a rule. So let's imagine we have the same twin experiment like this, and imagine that you are taken and then you come back. But there is this unfortunate rule that when they come back, they both should die. Now, which twin would you rather be? Would you rather be the twin that moved with constant velocity, or the one that had changing velocity and felt some acceleration? So you can think which one you would rather be. I think in this situation, you probably would rather be this twin that managed to live longer, and that was somehow moving with constant velocity, in this case, zero velocity. Now, that's what you would prefer. Now, it turns out that even basic particles prefer this. Even elementary particles prefer that. So elementary particles are trying to maximize their lifetime. And so that's basically why they move along straight lines. In some sense, that's why they move with constant velocity if there is no external force. You can view the result of that motion as the result of trying to, as them trying to maximize their lifetime, as happens with this case with the two twins. And that's one of the principles of physics for these particles. Now, so we described all of this just to explain that space and time really are combined together into a single entity that we sometimes call space-time. And the way we perceive time depends on how we move. So two observers that are moving differently perceive time in a different way. And that's why it's convenient to think about space and time together as this entity called space-time. Now, sometimes it looks a bit surprising that we're talking about space and time together. They seem very different, but the theory of special relativity sort of tells us that this is a single object. And then particles move in straight lines in the space-times, or they move with constant velocity to maximize their lifetime. Was there a question or no? Okay.
No questions.
Okay. Now, so there we described a bit the space-time and special relativity. So now we'll talk about something that looks at first sight slightly different, which is gravity. So in the old times, people said that people had the intuition, and that's the intuition from our everyday life, that heavier objects seem to fall faster. But then it was understood that everything really falls the same way once we remove the effect of air resistance. So if we drop two objects, they both follow exactly in the same way in the gravitational field of the Earth. Now, this observation led to an idea that Einstein called his happy thought, was the idea that when you fall freely, gravity disappears. Because if you are holding, let's say, something in your hand and you are falling, you and the object you are holding are falling exactly in the same way. So it looks like this object had its weight disappear. And he promoted this into a new sort of law of physics, sometimes called the equivalence principle, which basically says that if you are falling freely, there is essentially no effect of gravity. So that's why, for example, an astronaut and the spaceship, they're both moving in the gravitational field of the Earth, and they're attracted by the Earth, but they are falling essentially in exactly the same way. So they feel that there is no gravity, as if there was no weight. Now that idea, together with some other ideas, led to the development of general relativity. So this is Einstein's theory of gravity, which says that gravity is due to the geometry of space-time, and that if you have a heavy object, that object curves the space-time around it. And if you have a second particle, so a very light particle, it would follow the trajectory. So similarly to what we discussed for particles in flat space, that particle will follow the trajectory of maximal lifetime trajectory in that space-time. Now, something important about this is that gravity changes the flow of time. So time flows differently for two observers in a gravitational field. So for example, if we have two people here, one in the top floor of a building, the other one in the lower floor, the time will flow more slowly for the one in the lower floor than the one in the upper floor. And this happens because of the deformation of space and time that we were discussing. So when we say that a heavy object deforms the structure of space-time, one of the things this says is, in particular, that clocks will run differently at different heights. So this here I exaggerated the effect. So, but there is it's a very tiny effect here on the surface of the Earth. Is 1 part in 10 to the 15. But current clocks can definitely, the atomic clocks can really sense this difference, and in fact, differences of a few centimeters in height.
So Juan, is
Yeah.
this effect used in calculating time, like when we use all these GPS signals and all that? So there's satellites up there, and there are
Oh yes,
our
yes,
users
yes.
down
So yeah,
here.
this is definitely an effect that it's important. Well, first of all, we just mentioned that there are clocks that can measure this effect.
Yes.
So if you have a clock running on the surface of the Earth and a clock running in the satellite, so the GPS satellites are based on clocks that are in satellites that are sending regular signals. And by the timing of these signals, you can determine your position on the Earth. And it's necessary to take into account this effect as opposed to, well, this effect together with the effect of special relativity because the satellites are moving. And so once you take into account these two effects, you can really make an accurate precision of your position. So if you didn't take into account this effect, you would get your position wrong by large amount. So it's something that is used in everyday technology, if you wish.
Yes.
And yeah. Now there is a similar twin paradox, which is that if you have two twins and you bring one near a very massive body, because of that effect, the twin that is brought near the massive body will be younger. So similar effect, but due to the gravitational field or the curvature or the deformation of the geometry of space-time. Now, Schwarzschild found the geometry outside a spherical massive body. So if you have a spherical massive object, he solved Einstein's equations and found the full geometry. And that geometry in particular tells us how time flows. So there is some flow of time very far away, where the geometry is essentially that of flat space. And when you're at the surface of this massive object, time will flow a little more slowly. That's the same that we discussed for an object in the bottom floor on the Earth. And also, if you had someone standing here on the surface of this object, this person will feel some weight. Now, if you take that same star or massive body and you keeping the mass the same, you make it a little smaller. What you would find is that as you make it smaller, this effect of the slowing of the clocks becomes more important. So this clock runs more slowly, and this person feels a larger weight when he or she is standing on the surface of the star. Now, the surprising thing is that there seems to be a particular radius, which we now call the black hole radius, such that if the mass was smaller, if the massive object was smaller than that radius, then it looks like time has come to a complete standstill, that time is not flowing. And if you had a person standing there, that person would feel an infinite amount of weight. Okay. Now, this looks very weird, very strange. And this was the strange aspect of this solution that Einstein did not like. He said, no, this can't be true. This cannot happen. Now, it's important to realize that this person that is sitting, all these people we were discussing that were sitting on the surface of the object, they are not falling freely. Okay? So you can ask what happens if there is someone falling freely in this geometry. Now, it turns out that if they fell freely, then somehow the geometry actually continues beyond that surface, and you can continue behind somehow this particular surface that we call the horizon. And when you go to the interior looks a bit like a collapsing universe. So you don't feel anything special when you go through the horizon. So someone who's falling freely would not feel anything special at this surface. But then that person will encounter a region where space-time is collapsing, and eventually the space-time curvature becomes very, very large. So that means there are very big gravitational forces that will rip you apart. And you will die when you get to this so-called singularity. Singularity means that it's a region where the the space-time curvature is very large and where we stop trusting the equations. So the geometry inside is a bit like a big crunch. So it's the opposite of a big bang. It's a place where space-time is collapsing. So that's what we have inside black holes. Now notice that this singularity is really to the future. It's not a place in space, but it's somehow a location in time in the future. So that's where it is. Now, just to make an analogy and to explain this this feature that the horizon of what the horizon means, there is a very nice analogy which is to view space-time as a kind of river. So it's analogous to a river. Imagine that you have a river where the velocity of the water is slowly increasing as it gets then to a waterfall. The waterfall will be analogous to the singularity. Then there will be, in this river, there will be fish that can swim at some maximum velocity, which we will call the speed of light. So it's analogous to the speed of light. So here in this region where the velocity of the water is less than the maximum velocity at which the fish can swim upstream and will not fall into the singularity or into the waterfall. Now there is a particular location along this river where the velocity of the water is equal to the maximum velocity at which the fish can swim. And if you if a fish is swimming in this location, swimming upstream, this fish will not be able to escape. But on the other hand, it also will not be falling. It would be stuck there. And finally, if you have fish which is swimming in the region where the velocity of water is higher than the maximum velocity at which it can swim, then this fish will not manage to escape and will eventually fall into the singularity, into the waterfall in this case. So that's somewhat analogous to what we were discussing. And if this fish, let's say, live in if the water is mud, let's say has mud and cannot see the shore, this fish will not have any way of telling that they are crossing this point. I mean, if you have some fish moving in this river, they will not notice that they are crossing this particular surface. Is something that is somehow in our minds. It's not detectable by the fish that is swimming in the river. Okay. Now, there are a few things that we understood about black holes. It took many years to understand these things, but these are all features about classical black holes. The first is that once you cross this horizon, you cannot get out. It was also understood that the star can collapse into a black hole, and that typically is going to be the fate of stars that have a mass which is a few times the mass of the sun. And finally, it was understood that there are many objects in the sky that are black holes. Now, there are a few objects in the sky that are believed to be black holes. Some are produced by the collapse of massive stars, and there are also black holes at the center of galaxies. And how do we see them? So matter falls in and emits light or other radiation, or we also see gravity waves produced when two black holes collide. So
Masuk. Okay.
Hello,
Yeah.
sorry, can you please mute?
Yeah, okay. So this is some exciting news from recent years, which is that they are very sensitive.
What 1 minute, Juan. With the slide before this, you said we can see the gravitational wave. Can we detect them reliably?
Yeah,
The
so
gravitational wave?
Yeah. So let's discuss that. So
Okay.
So when two black holes are moving around each other, they produce vibrations in the shape of space-time, sort of ripples in the geometry of space-time that are waves. They are waves in the structure of space-time or the geometry of space-time. They're somewhat similar to waves that propagate, let's say, on the surface of the water, but in this case, they propagate in the vacuum, and they represent distortions of the shape of space-time. The same way that electromagnetic waves propagate in the vacuum and are distortions of the electromagnetic field. Anyway, so these waves are produced when two black holes are orbiting each other, and since black holes are very heavy, they really distort the space-time geometry quite a bit when you're very close to the black holes. But then these waves travel over cosmic distances from very far away, from, let's say, 1 billion light years away. And they reach here, the Earth, as very, very tiny little distortions in the geometry of space-time. And so you need very, very sensitive detectors that can detect this small deformation of the geometry of space-time. And
but what is a gravity wave? Is it what do you call a transverse wave, a longitudinal wave, electromagnetic wave?
Right. Well, gravity waves are transverse waves. They if the wave comes and you have some distribution of masses, let's say the masses are forming, let's say, a little ring, so the wave will deform them, will squash the masses up and down with a quadrupolar pattern. So that's basically what they would do to the masses, or they do that to the Earth as they pass through, but this deformation is very, very, very small, sort of like one part in 10 to the 20. So very, very tiny. So you need very, very sensitive detectors that are very big interferometers that, yeah, I guess I wasn't planning to discuss it in great detail, but I could give more details if you want.
Okay. Do they travel at light speed or some other velocity?
Yeah, these waves travel at the speed of light.
Oh, okay. That's interesting.
Right. Yeah, so okay. In that way they're similar to electromagnetic waves that also travel at the speed of light. In fact, in some cases, these collisions are not between two black holes, but between neutron stars, which are some other objects. And when the neutron stars collide, they produce a big explosion, and they also generate light. And so we can see both the light from the neutron stars and the gravity waves, and they reach the Earth essentially at the same time. So that's one way in which we can really see that they're moving at the speed of light. Okay, so this is this slide I was discussing some observational aspects of black holes, and I would say that we are now in this last few years, we're in a golden age for observations of black holes through gravity waves and also through some other experiments that I have not discussed. We are really getting to see black holes in more detail right now, much better than we were able to see them, in the past century, in the 20th century. So they are now, there's now a lot of evidence. Well, they are now real objects in some sense, more real than they were before. We have very direct evidence, and we'll have more as these experiments get more and more sophisticated. But now I will not discuss these observational aspects, and I will discuss some theoretical aspects of black holes, which is the field I work on. Of course, these observational aspects are, of course, very interesting. And if you have questions, we can discuss them a bit more. So these are interesting because of their conceptual aspects. I'll try to explain why they're interesting. First, I discuss some interesting classical properties of black holes. One is that the black holes are very universal in the sense that the final shape of a black hole is independent of how it was formed. So it only depends on the mass, the angular momentum, and its charge. So for example, you can have different stars that are different colors, made of different materials, and so on. And if they collapse into a black hole, they will form the same black hole. The black hole will be identical in all these cases. If the stars had the same initial mass, then the black holes will be the same. So they are simply characterized by the mass, the angular rotation velocity, and its charge. Most of the astrophysical black holes have no charge, so it's basically the mass and the angular moment, the angular velocity. Now there's another interesting aspect of black holes, which is the following. So we discussed a moment ago the collision between two black holes. And so when two black holes collide, the two black holes collide and form a bigger black hole. And in the process, they emit some gravity waves. Of course, these gravity waves carry some energy. And there was some initial energy in the two black holes, which is related to the mass of the black holes. So the famous formula E equal mc squared. And so what that means is that the mass of this final black hole is smaller than the sum of the masses of the two initial black holes, because part of the energy contained in these black holes got emitted as gravity waves. So, I mean, it's in some of these collisions that we were discussing, there is an amount of energy in the gravity waves, which is the equivalent of the energy of, let's say, a few solar masses. So it's a lot of energy that goes into the gravity waves. However, if you consider the areas of the black holes, Hawking showed that the areas of the black holes, the area of the black hole horizon, we are considering the area of this surface, which we are calling the horizon, which is divides the region that is collapsing inside from the exterior. If you calculate the areas before and after, you find that the area of the final black hole should be always bigger than the area of the initial black hole. So the mass of this black hole cannot decrease so much that the area somehow becomes smaller than the sum of the areas. So far we've discussed the black holes according to Einstein's theory. Well, maybe I should say one more thing about this. So what this is interesting because it's a very simple law that emerges out of a rather complicated equation. So Einstein's equations are equations which relate the geometry of space-time to, well, that constrain the geometry of space-time, and they're quite hard to solve. I mean, they can be solved using computers and so on, but they are somewhat difficult to solve. However, this is a very simple law that comes out of these equations, that you don't need to solve the equations to show this law. So far we discussed black holes according to Einstein's theory of general relativity, which is a classical theory. And when we include quantum mechanics, we find a new surprise. So quantum mechanics is the type of physics that we use to describe elementary particles or atoms or objects smaller than atoms. Now, this new surprise that we find is that black holes can emit thermal radiation. And the temperature can increase when the size decreases. So if you have a black hole of some size, it will emit radiation at some temperature. As you make the black hole smaller, the temperature will become higher, and you could make it small enough that the black hole will look white. It will look white to our eyes. So this is a very surprising effect because black holes were called black because they were not emitting anything. Even light could not escape. But now we find that the small enough black hole could actually look white because of this quantum mechanical effect. So in some sense, we had this effect is so surprising that it implies that black holes had the wrong name.
But Juan, a thermal radiation is an electromagnetic wave, right?
Yes.
A very long
Yes.
electromagnetic wave. So if light and radio cannot escape, how does thermal EM escapes?
Yes. So I'll explain in more detail what's the rationale for this effect.
Okay.
What can happen?
Right.
So
Sorry.
So basically, the classical laws of physics imply that nothing can escape and the black hole will look white. It will look black, sorry. But once you include quantum mechanics, there will be an effect that has to do with the fluctuations of quantum fields near the black hole horizon that imply that particles can escape to infinity and will be seen from far away. They can escape from the black hole and will be seen as thermal radiation coming out of the black hole. Now, when we say thermal radiation, you just mentioned that it would be very long wavelength. And that's true if the temperature is, let's say, room temperature or not very high temperature. But if you have some object that is very hot, let's say the temperature of the sun, the surface of the sun, so let's say 7,000 Kelvin, then that will look white. I mean, they will be so hot that you'd see it as the surface of the sun. You see that color, essentially white. And that would be the case for a black hole that has the size of a bacterium. So very tiny black hole, let's say half a micron, will have this type of temperature. Now, there are no black holes that are this small that are produced naturally, as far as we know. So the black holes that are produced naturally through astrophysical processes tend to be black holes that are very, very heavy. They have masses of order the mass of the sun or higher, maybe 20 times the mass of the sun, 100 times, 1,000,000 times, 1,000,000,000 times. And those black holes would have very, very tiny temperature. So for a black hole that has the mass of the sun, the temperature will be 0.00, many zeros above the absolute zero of temperature. So this is in degrees Kelvin. So this is a tiny temperature. It's smaller than the temperature of, let's say, than the temperature of the cosmic microwave background. So this is some effect that cannot be seen, or it's irrelevant for astrophysical black holes, but would be relevant if we had very tiny black holes. And it's conceptually important, as I will mention it later. So, but what I'm saying right now is that this is an effect that was predicted theoretically by Hawking, but has not been seen in black holes because of the fact that for the black holes that are produced naturally are very big, where this effect is very small. But I guess I probably should mention that there is a rather similar effect that is relevant for cosmology, and that effect has been seen, or we see some of the consequences of that effect in the formation of structure in the galaxies and the galaxies. Okay, so now I promised that we'll discuss a bit the origin of this effect. So the origin has to do with the relativistic quantum mechanics, which is the laws of quantum mechanics together with the laws of special relativity. And one of the things that this theory tells us is that particles can be created and destroyed. And in fact, the vacuum is a kind of complicated object according to this theory of relativistic quantum mechanics. So you constantly have pairs of particles that are produced and annihilated. So in principle, the vacuum has zero energy. But you could have, for very tiny instances, particles which have, let's say, one has positive energy, the other one has negative energy. And they are possible because of the uncertainty principle. So for a tiny time, you could have fluctuations in the energy. And you could imagine that there is a kind of policeman that enforces the law that you cannot, that the energy should be conserved, and that particles cannot have negative energy. But if the negative energy exists for a very tiny time, then the policeman allows that, because that's consistent with the uncertainty principle. So, I mean, by this policeman, what I mean is the laws of physics. So you can have negative energy for a short enough time, but the particles should annihilate again soon, otherwise they will be in trouble, because they will run into trouble with the policeman. And what that means is that in flat space, there is no net particle creation. So you have these pairs, but they're constantly annihilating, so there is nothing. Now, something different happens when you have a horizon. So what this picture represents is that this vertical line is the horizon. What is to the left is the interior, and the exterior is to the right. So if you have one of these pair creation processes occurring there, from the point of view of the outside, the particle here inside has negative energy, okay? However, from the point of view of the policeman inside, has a kind of different notion of energy because of the big distortion of the space-time geometry. And what looks like energy from the point of view of the policeman outside looks a bit like momentum or velocity, let's say, from the point of view of the policeman inside. And the policeman inside has no problem with particles with negative momentum. So it allows this particle to exist. The policeman allows this particle to exist, and then this positive energy particle is free to propagate all the way to infinity or far away from the black hole, and will be seen far away from the black hole as thermal radiation. So there is some net particle creation. So what this implies is that if you had one of these small black holes, as it emits radiation, it will lose energy, so it will lose mass, and the black hole would then have a finite lifetime. So what are the lifetimes of various black holes? Well, a black hole of the mass of the sun or the Earth will live much longer than the age of the universe, so this is not a very important effect. If you had a black hole with an ordinary mass, let's say 100 kilograms, it would evaporate in a very, very tiny fraction of a second, and it would be an explosion worse than a nuclear bomb. So it's a very big effect for such a small mass black hole. Now, fortunately, we don't have these small mass black holes lying around. But this is what the theory predicts. And if we had a black hole of the mass of roughly the mass of a mountain that was produced in the beginning of the Big Bang, it would be evaporating now. So those are some black holes that you perhaps might be able to observe through this effect, though none have been observed. Now, this effect leads to some theoretical problems with the black hole temperature. And these thermal properties mix quantum mechanics and gravity and leads to some puzzles. So the puzzles are, why are black holes hot, and the problem of information. So I briefly will discuss these two puzzles. So when we encounter some object that has temperature in physics, so we know since the 19th century that temperature has to do with the motion of the microscopic constituents of matter. So you have, let's say, a box or a room full of air, and the air is colder in this room and hotter in this room, then what that means is that the molecules are moving more slowly in the cold one than in the hot one. So that's the difference between the two. And so we explain heat as due to the microscopic motion of the constituents of matter. Now that's the fundamental way in which we explain heat in physics. And we have a related concept, which is called entropy or information, which gives us the number of configurations of the constituents. And the first law of thermodynamics gives us the entropy or the number of states if we know the energy and the temperature. And so we can apply this first law for the black holes, and it gives us that the entropy or the number of configurations of the constituents of the black hole is proportional to the area of the black hole horizon. And in some units of length, which is a combination of g Newton, h bar, and the velocity of light, which I set to 1 in this formula, and it works out to be a number of order 10 to the minus 33 centimeters. So this is a very, very, very tiny distance. So that means that the macroscopic black hole has a very, very large entropy, much, much bigger than the entropy of any ordinary object of the same size. Now, there is another law of thermodynamics which says that the entropy should always increase. And we already saw that Hawking had proven the area law, which is the fact that when you have black hole collisions, the area increases. And we see that there is this interesting sort of consistency condition, if you wish, or relationship between the equations of general relativity in the context of black holes and the second law of thermodynamics, which are things that come from very different areas of physics. And so it's rather theoretically surprising that these two things that are unconnected with each other are related through black holes. So this raises the question of what are the constituents of the black holes. So they should be the microscopic constituents of space-time. If you wish, they are like the atoms of space-time. They should be they should tell us something about the structure and nature of space-time. Recall that black holes are independent of the matter that forms it. Could be a star, it could be, maybe even you could make black holes out of just pure radiation in principle. So, okay, so that is one of the issues. The second issue is this issue of the information loss. So you can form a black hole in many different ways, but it looks like it always evaporates in exactly the same way by emitting this thermal radiation that appears to have no information. But in quantum mechanics, if we form things in different ways, then what comes out should also be different. And it might be that things are approximately thermal, but they should not be exactly thermal. There should be subtle differences in the outgoing radiation, which carry the information of how the black hole was made. So in order to answer some of these questions, we need a theory that puts together quantum mechanics and gravity. And that theory is, well, one candidate for that theory is the so-called string theory. I will not discuss string theory. It's a theory under construction, and it's a theory that describes the quantum mechanics of space-time. It reduces to Einstein's theory under ordinary circumstances, which is long distances or low energies. And there is one aspect that I will discuss, which is that it can describe in a complete way certain simple universes with special covers. So there's some special situations, special universes, which we can describe completely. And in those universes, we can consider black holes and answer some of these questions. And this is the subject it's called holography, which says that we can describe the interior of certain spacetimes in terms of a theory on the boundary. And the theory of the boundary is a theory of strongly interacting particles. This is kind of a picture of this negatively curved spacetimes. So this is a map from the negatively curved spacetime to the flat screen of your computer. And each of these fish has the same proper size. And you have this accumulation of fish here because we are mapping a curved surface to the flat surface of the screen. So that's similar to how we are mapping. When you look at the world map, the regions near the poles near the North Pole or the South Pole appear stretched. So this is a picture that tries to represent the same thing. So we can have in the interior, we can have gravity and some object moving in the interior. And that object is described in an equivalent way by some particles that are moving on the boundary. And so here, I've represented these particles with this jittery motion, trying to represent the fact that these particles are strongly interacting with each other. They are colliding and so on and being produced in these collisions with each other. Now you can describe any object that moves in the bulk. In particular, you can describe black holes. And black holes correspond to a large number of particles that are moving on the boundary. Actually, it should be a fluid or a continuum of particles, all strongly interacting. Here, in making this graph, I got tired of adding new particles, but it should be completely full of particles. And they are moving, and they are the things that are giving rise to the temperature and entropy of the black hole. So in this description, we understand where the heat and entropy of the black holes are coming from.
Yeah, Juan, in that sorry to stop. In that
Yes,
picture
no.
that you showed, allow me to understand a bit more further. The particles are moving on the surface of the black hole or at the event horizon?
Okay. Yeah, very good question. So let me, I think I should have explained this a little better. So this is a picture of a negatively curved space-time.
Yes.
There is an infinite number of fish when you go from the center to what we are calling the boundary. So the boundary is really infinitely far away, right? So this is, if you wish, an infinite universe, very large universe in space. This is a spatial slice or a spatial moment of equal time in this universe. And so the universe is very big, but it's negatively curved. And if you were to project it to a flat surface, there is this region, which is in principle infinitely far away, which we call the boundary, okay? So then what we do is we consider a black hole that sits inside this universe, okay? The black hole has a finite size, but there is still an infinite distance to the boundary. So the boundary is very, very far away. So these particles that we are discussing now are not in the surface of the black hole, they're really living very far away. And they describe not only the black hole, but the whole space-time of this universe, right, that describes this universe. Is that more clear now?
I understand now, yes, thanks.
Sure. So this theorem on the boundary obeys the rules of quantum mechanics, and then that implies the black hole in the interior should also obey the rules of quantum mechanics. And that's why we were saying in the very beginning that we think that these rules of string theory tell us that black holes follow the rules of quantum mechanics. Now, what I will do in the next few slides will be to try to explain this idea that out of the motion of the particles on the boundary, we can get the geometry of the interior. So that the idea is that in this description, the geometry of space-time is what we call emergent. And I will try to explain what this means. And we'll do that through an analogy.
1 minute, Juan, there's a question from Mr. Anwar alias. Mr. Anwar, I would like to ask a question.
Yeah, go ahead.
Later, I could ask you later on, maybe when we talk about singularity.
Okay, all right. Okay, all right. All right then. We'll continue then.
Okay, so we'll do a certain analogy. So let's consider a sentence. So this is some random sentence. Let's say, if a man does not keep pace with his companions, perhaps it's because he hears a different grammar. So just some sentence. Now, when we hear this sentence, we, in our mind, we're dividing it into words, right? And we are analyzing and parsing this sentence. And then we are grouping these words into words that are forming various grammatical units. So maybe the subject and the verbal phrase and so on. And these grammatical units form also bigger units, bigger clauses and so on within the sentence. And in addition, there are words in the sentence that are correlated. So for example, the word man, his, and he are correlated. They are all related to each other. The notion of keeping pace is also correlated with the word drummer. That's a kind of deeper correlation. But when we hear the sentence, we made all this, well, we analyzed the sentence and we perhaps subconsciously did this whole analysis. And so in some sense, there is a certain other dimension that appeared in this analysis, which is this direction of the depth of the meaning of the sentence. So as we go to bigger and bigger grammatical units, we understand more and more of the meaning of this sentence. And so we can think of the direction sort of that goes from the sentence down in the screen as some extra emergent direction that comes out of the correlations between the words and the meaning of the sentence. So in this analogy, we can think of the particles or the quantum system at the boundary. The state of the quantum system at the boundary is like a very, very long sentence, okay? And then the idea is that the space-time is kind of doing a grammatical analysis or is exploring the meaning and the correlation between the words of this sentence and is giving rise to this extra dimension. And if we have some particular words that are particularly correlated, then they're related to particles that are moving in this spacetime. So that's somehow the analogy. Now let's discuss what is analogous to a black hole in this spacetime. So for that, we'll go back to the same sentence, and we'll start making some changes. So for example, here, we change some of the words. For example, here, the words that are in pink are the ones that have been changed. And we lost some things. We lost some of the correlations. For example, the word man and its and she are not really correlated anymore, or the word keep pace is not correlated to lecture. So we lost some of the correlations we had. And if we make more changes, then the sentence kind of makes sense locally, but part of the meaning of the sentence is lost. So now the whole sentence now that does not quite make sense. So you can read it. So if a man, my nurse mother, pays its companions, the moon tells me she writes a different lecture. That's not a sentence that really makes sense. And there what we say is that there is a kind of horizon of meaning. So the sentence makes sense up to a certain level, but then it ceases to make sense at a certain level of analysis. And as you keep changing more, let's say you change all the letters at random, then it just doesn't make any sense. So this horizon grows, the black hole grows, and the area of the black hole horizon is analogous to the ignorance, so the amount of things you don't understand about the sentence. And the idea that the area should grow, or that the entropy should grow, is analogous to the idea that if you start changing words randomly in a sentence, you are more likely to mess it up than to make a nicer sentence. You're going to, if you did it randomly, you will get something that doesn't make any sense. Now, imagine that these changes that we had here are produced by a reversible process. Let's say something similar to an encryption algorithm, the type of algorithms that are used to send secret messages through the internet, that take what you type and then they make something that is all garbled, somewhat like this. But when it reaches the recipient does the inverse transformation and can extract your message. So that's a reversible process. And in that case, we can reverse the process and recover the original sentence, right? And the idea is that the laws of physics on the boundary change the state of the boundary, change the configuration of the particles that we have on the boundary. But it's analogous to an encryption process in the sense that it is reversible, because the laws of physics are reversible. And so at least in principle, we can undo the formation of the black hole and recover the original information that fell into the black hole. Well, I was planning to say a few more things about holography, but since we are at the end of my time, maybe I'll just skip many of these questions and I'll go directly to the conclusions. So we learned that black holes are fascinating objects where the geometry of space-time is deformed in a dramatic way. And black holes and quantum mechanics give rise to interesting theoretical challenges. And string theory is a theory of quantum gravity that can describe black holes in a consistent way, at least as seen from the outside. And space-time, in this description, space-time is an approximate concept which arises from more fundamental elementary particles living on the boundary of that space-time. And I discussed in this analogy, I mentioned that there is a correlation between words. In the quantum system, what we have is a type of correlation that is called entanglement, which is a quantum mechanical property. And that quantum mechanical property is crucial in determining the structure of space-time, this description. Okay, thank you.
Okay, thank you, Prof. Juan. That was very curved. Okay, there are a few questions. on the internet. Sorry, on the a few questions. Okay, what is the best approach to understand black holes? String theory or loop quantum gravity?
Well, I think string theory has given us more insights about black holes and is more developed than what we can learn from loop quantum gravity.
Okay, okay, that is one. There's a question by Mr. Izzat Zubair. Does the Hawking radiation contain any information about the black hole?
Yes, so in the simplest approximation, which is in the approximation that Hawking calculated it does not contain any information. But when you use these holographic descriptions, then you can calculate what the state of Hawking radiation is, and you can it will contain the information about what fell into the black hole.
Hello, can I ask a question?
Yeah, just a minute. Just a minute. There's one more question by Izzat that I'd like to finish up first. Okay, Izzat also asks, is it currently possible to detect evaporating black holes from background noises?
No. Currently there is no detection of any evaporating black hole. I mean, part of the issue is the type of matter we have in our universe tends to produces black holes that are very big. That is related to the fact that protons or neutrons are very, very light compared to the so-called Planck scale. So they're in some sense big objects. And so you need to put lots and lots of them for them to collapse into a black hole. That's basically why that's where this solar mass number comes from. That the black holes that are typically formed are solar mass or higher. If nature had some elementary particles of very much higher masses, then we could have black holes with lower masses. So we need to put less of them to form a black hole.
Ivan, the floor is yours.
Now, so the matter in our, the matter that we know does not produce small black holes. There might be matter that we don't know that produces small black holes, or it could be that small black holes were produced in the beginning of the universe.
Are you saying that there are some types of matter that we have not classified yet?
Well, there are. Well, we know that there is dark matter.
Okay.
It's some particle. We don't know what that is.
Oh yeah, that is, yeah, correct.
Now the leading theories are that those particles are not very heavy for what I'm talking about. So I personally don't think that they would form black holes, or I mean, it's not ruled out that they could be like tiny little black holes, but it's not the most likely explanation. And it's yeah, I don't want to say that that's a possibility. It's a very remote possibility. Very, very remote possibility.
Okay.
But another also, I would say, remote possibility is that maybe black holes were produced in the beginning of the universe. So in the beginning of the universe, there were violent processes that perhaps could have produced black holes of relatively small masses, which maybe are now evaporating and so on. So that's one way in which you could see this effect. Now, the reason we study black holes and this effect for black holes is mainly to understand how quantum spacetimes work. So it's just to solve the theoretical puzzles and eventually to understand enough that perhaps extract some of these lessons and then apply them to cosmology. So I think the place where quantum gravity or quantum spacetime is going to be most relevant observationally, I expect that it will be through quantum cosmology, so through cosmology. And in fact, I mentioned in passing that there is an effect similar to the Hawking radiation effect that operates in the very early universe. And that is something that created in the beginning of the universe some small perturbations in the fabric of space-time, that in the density of the matter, the beginning of the universe, that then grew to form the structure in our universe, so the galaxies and planets and so on. So that's the theory of the current best, the most accepted theory, or the leading candidate for a theory of the formation of structure. Involves quantum effects that are similar to the Hawking effect for black holes, but applied to the early universe. So that's an example where something that was learned from black holes got transferred to cosmology and is now an important part of our understanding of cosmology. And we hope that by understanding more aspects of black holes, we can, again, extract further lessons for cosmology that perhaps we can observe. So I think it's more likely that we will observe some interesting quantum effect through cosmology than through black holes, because of what I was saying before, that nature doesn't very easily produce small black holes. But we do know that the universe was very small when at the beginning of the Big Bang. So we know that these quantum effects were important then.
Okay, I'll come back to that. Ivan?
I want to thank Professor Juan Maldacena for the interesting talk. I have a couple of questions. The first one is, if the ordinary mass black holes are so hot, as you mentioned, they would be worse than a nuclear bomb.
Yeah.
What are the signatures that the accelerators are trying to find about Hawking radiation? Let's say some accelerators, some experiments are trying to find direct evidence of Hawking radiation, but in which way?
Well,
are they trying to find?
I think people had speculated that perhaps you could make very tiny black holes in accelerators. Those would be black holes not of 100 kilograms, would be black holes with the mass of elementary particles, so very small, and they would evaporate almost instantly. Now, those black holes were not seen in the accelerators, so there's no evidence of any black hole in an accelerator. That's maybe a possibility, but not one that has been realized in nature so far. It requires the existence of extra dimensions of space-time, large extra dimensions. So extra dimensions that are relatively large. That's one of the things it requires. And so those things were not seen. So that is a very speculative possibility.
Sure. My second question has to be with the analog models. You mentioned the fish example, and I know there are some analog models developed by some international researchers, including William Unruh, who claim to have found some signatures of Hawking radiation in fluids. So I would like to listen your opinion about it. What do you think?
Yes. So I think this model. So this analogy of the river that I mentioned, that was due to Unruh, the person you just mentioned, and I think he and some collaborators have been constructing sort of fluid flows and so on that could display this effect, and you understand that they've seen this effect, so that the effect similar to Hawking radiation. I think that's interesting, and it's an effect of, let's say, seeing particle production in time-dependent configurations. It's an effect that arises in many other situations. But it definitely captures some aspect of black holes, which is this Hawking radiation, but not all aspects. So, for example, this aspect about the entropy that we discussed is not captured by those fluid analogs. I should mention that there is, I would say that something that we think captures all the aspects of black holes are this holographic description. So a holographic description, if you wish, is some analog situation, right? Where you could, in principle, with a very complex quantum computer, you could or quantum simulator, you could build a system that has strong enough interactions so that it has an equivalent description in terms of a black hole. It wouldn't be a black hole, a four-dimensional black hole in our universe, but it would be a black hole in this universe that is emergent out of the interactions. That's, I think, if you wish, in the class of these analog systems, which I think would capture basically all aspects of black. We think it would capture basically all aspects of black holes. And
thank you, ma'am.
And
yeah,
so you can estimate how complex those computers would be. So I think if you had a quantum computer that has the number of qubits and the number of gates that could break the encryption algorithms, the current encryption, classical current encryption algorithms, those numbers are similar to the numbers you would need to simulate the tiniest, let's say, black hole that is described by Einstein gravity. So in a toy model universe.
Yeah, and my final question is, what is your proposal for the solution of the information paradox? I mean, I assume that is based on the holographic principle, because we are dealing with a mixed quantum state, no? When the radiation
So
basically is
yeah. So holography and these models that we were discussing are examples where we see that information comes out of the black hole and allows you to compute the state, right? But as currently understood, they are not giving us a very precise picture of what happens in the interior of black holes, and in particular, the singularity. So I would say that there are still things that remain to be understood.
okay, thank you.
Yeah.
Thanks, Ivan. There's one question by Prof. CT. Thanks, Prof. Maldacena, for sharing interesting concepts in general perspective. The question: suppose an entangled pair of quantum particles are also entangled respectively to quantized space-time entangled states. Would this multi-entanglement be useful for explaining ER equals to EPR duality? Could this explain non-locality? Thank you.
Okay, yeah. So this is
the question is on the chat. Yeah.
Yeah, I saw the question in the chat.
Yeah.
So, well, this is a topic I really haven't discussed. So I barely touched the surface of this connection between gravity and quantum mechanics. And we think that there is a deep connection between concepts of entanglement and the geometry of space-time. And so there are some geometries where you have, maybe I can show the picture. So there are some geometries where you have black holes that are entangled with each other, and the corresponding geometry will contain black holes which are connected through the interior, black holes which are sharing an interior. And so this suggests that there is a connection between entanglement and the geometry of space-time. And in this context, it's called the ER equal to EPR. ER is Einstein and Rosen, who were the first to realize that you could have black holes that share a single interior. So they are connected through a kind of wormhole. And Einstein, Podolsky, Rosen were the first who discussed entanglement. And these two seem to be connected. So ER equal to EPR duality is like a principle or an idea that is not yet fully understood, but we think that it's a principle that should be incorporated by any complete theory of quantum gravity. Okay. I think that's all I would say about this topic for now.
Okay, there's another one in the chat. Thank you, Prof. Maldacena, for the interesting lecture. Can you discuss some aspects of how the study of heavy ion collisions and QCD, quantum chromodynamics, could possibly inform us more about the nature of black holes?
Well, I think usually the information in that context goes maybe the other way. that black holes can be a model for heavy ion collisions. Okay, let me first explain what heavy ion collisions are. So in accelerators such as the Large Hadron Collider, people collide very heavy nuclei of, for example, lead, that will contain many protons and many neutrons, and they collide them at very high energies. And when they do that, they produce a new phase of matter where all the nuclear particles, the protons and neutrons, sort of lose their identities, and you form a kind of quark and gluon plasma, is called, or quark and gluon liquid. And so you form this new phase of matter, very hot phase of matter. We think we had that hot phase of matter in the beginning of the universe, by the way. That's one reason they are studying it. Now, all these quarks and gluons are interacting fairly strongly, and you can model this system, or you can. This is something that is not very easy to solve analytically. In principle, we know the laws that govern this motion, but they are hard to solve in practice. So what is done is that people imagine this collision not in QCD, but in a theory similar to QCD, but that has a known gravity dual description. And in that gravity dual description, what happens when you do this collision is that you produce a small black hole. And then you can use the black hole to understand what will come out of the collision and the properties of what comes out. And it's a black hole in a weird 5-dimensional space. And it leads to an interesting connection between black holes and hydrodynamics and so on. And so you can use it as a toy model to try to understand QCD and the quark-gluon plasma. But it's a bit limited because you cannot do this directly for the theory of strong interactions or QCD, but for a similar theory. So it's what in physics we call a toy model. So some model that is exactly solvable, that is similar to what you want to study, but not exactly equal. So it's a whole art and science to extract the right lessons from these toy models. But that's what's been done.
Does this artificial particle accelerator black hole, the size is so small, so it evaporates very fast, as what you said earlier? Does this fall into that category? The area?
Well, yeah, at some level it falls into that category, and at some other level it's slightly different. So so the people who suggested that you would have black holes in the Large Hadron Collider were thinking of flat extra dimensions and producing really Schwarzschild black holes that could be described by Einstein's theory of gravity. Now, the things that we are producing in the LHC are this quark-gluon plasma that, as far as we know, it's not described by any known Einstein theory in any space. It's just described by QCD, and we don't know an alternative description. So in that case, in order to have the alternative description, you have to change the theory. So you have to imagine you don't do this in nature, but in some other alternative theory, which is something we often do in physics, that we don't solve the problem that we really have, but a similar problem that we can actually solve, and we extract lessons from this.
Okay, back to Mr. Anwar alias, if you wanted to ask something. Mr. Anwar.
Okay, thank you, Prof, for willing to come here and give very beautiful talks. Okay, I would like to ask you on my things on singularity. Some of the things that I'm still not so clear. Do you think the singularity can be described? Is it as super dense toward infinity, combination or collection of compact ensemble of closed string gravitons?
Well, the short answer is that we don't know how to describe the singularity. I mean, the classical, of course, according to general relativity, we get that the curvature of space-time goes to infinity. So but infinity is not an allowed value. Somehow it means that the theory breaks down. Quantum correction should become important, and we don't know exactly what we should say. So it's something.
The other one, which is more likely to exist, is it singularity or some kind of wormhole through? From your opinion.
Well, I think what you're asking is whether there could be some time beyond the singularity. So singularity looks like an end of time, and we don't know what comes after, if anything comes after. I really can't say. The honest answer is that we don't know. The perhaps prevailing view is, or well, one common view is that maybe time ceases to make sense, and there is nothing beyond the singularity, but that's we don't really know, so that might not be the case.
Okay.
I perhaps should emphasize that we would very much like to understand what happens at the singularity, because we mentioned this is similar to a big crunch singularity, and the Big Bang is the time reversal of that. So it's the opposite of that, in the sense that singularity is in our past as opposed to in our future. But we think that we are understanding the singularity is one of the main reasons why we're interested in these black holes, because then we could understand perhaps the singularity in our past, of the Big Bang singularity. That's the main motivation to understand quantum gravity.
Anwar, any more?
Okay. Okay, good. Thank you, Prof.
Okay. Okay. There's one more by Mr. Ashraf. Does the concept of black hole growth and evaporation at the same time contradict each other, or do we need both to happen at the same time?
Right. So according to the classical theory, so things can fall into the black hole, but nothing can leave, right? So the black hole mass should always increase. That's according to classical general relativity. But once we have quantum effects, the black hole is emitting radiation, the mass can slowly, can decrease. And these are two effects that we have. I mean, whether we have more of one or the other depends on the circumstance. So for black holes that actually exist in our universe, like these black holes that are colliding, or the black holes at the center of galaxies, all those black holes are in the regime where their mass is growing. So they are receiving matter and they are not emitting anything. They're emitting very tiny amounts. So they are receiving much more than they are emitting.
Okay. Any more questions by anyone?
Can I ask a question, please? Thank you.
Sure.
Oh, thank you.
But may I know who's speaking, please?
I'm Paulus. I'm coming from Indonesia.
Okay, all right. Carry on, sir.
Yeah, thank you very much. Thank you, Professor. I'm very new in this kind of black hole physics, so I just be pulled by some of my colleagues to do this research, and I am aware that there's a sort of conjecture. They call it as a weak cosmic censorship conjecture, which says that the singularity of the black hole always hidden inside the horizon. And
yes.
And during my research in these few years, yes, some people said that this conjecture can be violated, and some said it cannot. Yeah, and all of them give the proof of the calculation, which seems quite logical. Yeah, what is your opinion about that?
Right. So in higher dimensions, like in 5 dimensions, we know it's not true. So people have found configurations where where this is violated in a generic way, that you produce singularities. The singularities you produce are somehow very mild, so they are not as somehow strong as the singularity in the interior of the black holes. In 4 dimensions, I think people have shown, I think Christodoulou has shown that, or Choptuek, I don't remember. Okay, so somebody has shown that you produce singularities if you fine-tune the conditions. So if you have to send matter in the right way to produce a singularity.
Yeah.
If you send a little more, a little less, you don't produce a singularity. So the conjecture is, as originally stated, was wrong. In 4 dimensions, there is a conjecture that you generically produce a black hole horizon, but yeah, that's a conjecture so far, as far as I understand.
Okay, so what you mean is it might happen in 4 dimension, right?
What might happen?
The violation of conjecture.
Yes. Yeah, we know the original conjecture, we know it's violated. That there's a modified conjecture which adds the word generic, so that if you have generic initial conditions, then you would produce a horizon. The singularity will be behind the horizon. But even that, we don't know whether it's true or not.
Thank you very much.
All right.
I don't see any other questions coming from anywhere else. So Prof, we'll end our discussion here, and we thank you very much. But before you leave, just hang on a bit. We'd like to take a photograph with everybody present on the Zoom platform. So if everybody could please switch on your cameras. Quite a number of cameras are still off, please. Could you please all switch on your cameras? Ladies and gentlemen, cameras, please. Quite a number of cameras still off. Okay, that's nice. You can see it. All right, thanks for joining. Okay. All right, Prof City. Okay, Shah. Everybody say cheese. All right, say cheese. Thank you. Okay, thanks, Prof. Thank you. Good night.
Okay, thank you.
Thanks. Good night.
Thanks a lot.
Thank you all for listening, and best wishes. Yeah.
Thank you. Thank you
very much.
Yeah.
Thank you very much. Have a good day. Have a good night.
Yeah, you too.
Yeah. Okay. Bye.
Goodbye.
Okay. For the rest, I think there'll be a QR code session for attendance, especially for UNIMAP people.